Hello everyone. Today I'll introduce Realtek's dashboard solution in detail. Through this session, you'll quickly grasp 3 key points: the core functionalities of the dashboard, how to set up the development environment efficiently, and practical tips for customization. We'll cover everything from the overview, hardware requirements, wiring, feature configuration, experimental verification to software design. Let's get started. First, let's get an overview of the SDK. Our dashboard solution includes real-time speed display, a complete GUI framework, and a messaging system, along with rich APIs to accelerate prototyping and customization. The hardware core uses high-performance SoC like RTL8773 EWP, which connects to smartphones via Bluetooth, synchronizing data such as speed, navigation, and music playback status to the display for seamless integration. The second part is requirements. To run the dashboard application smoothly, you'll need the following hardware and software resources. The hardware setup includes an EVB motherboard, EVB, and display screen. For software, we provide the dashboard SDK along with specialized tools like the Image Convert tool, which quickly transforms images into binary formats, all ready for immediate use. The next part is wiring. Wiring is straightforward. Focus on 2 key steps: power configuration via jumper caps, and mode switching between download and working modes using dip switches. Detailed wiring diagrams are provided in the documentation. Just follow the steps, and you'll complete the setup in a matter of minutes. Different customers have different functional requirements for dashboard applications, and we provide a convenient configuration method to turn on and off existing features. Customizing features is as easy as flipping a switch. In the app_flag.h file, you can enable or disable specific functions by modifying macros. For example, set BLE HID device support to 0 to exclude Bluetooth HID-related code. More options are available in the dashboard demo support macro. The code size automatically optimizes after your changes. After the feature configuration is done, we can proceed to the build and download phase. 2 critical notes for building. First, the project is located in the EVB RTL8763 EP dashboard directory. Second, ensure the dashboard demo support macro is predefined in the preprocessor for feature configuration to take effect. When flashing, include both the application bin file and the user data file containing fonts and images, which are stored in the Bank 0 and Bank 1 folders. Of course, we also support the use of JLink for download and debugging, which is located in J13 SWD. After flashing, let's move to verification. Switch to working mode and press reset. The display will light up, showing a running dashboard with simulated speed values, battery indicators, and turn signal animations. For production, simply replace simulated data with real signals. Through the proprietary protocol or ANCS, real-time message notifications like SMS and WeChat can be displayed directly on the dashboard interface. When receiving calls, the interface will show incoming call notifications and enables call answering and ending functionality. Furthermore, the Realtek dashboard solution incorporates navigation mirroring capability. Through our proprietary protocol, navigation data can be transmitted from smartphones to the dashboard for real-time guidance. The system offers 2 display modes, a streamlined basic mode and a feature-rich advanced mode, providing users with flexible viewing options. Next is a brief introduction to our software design. The source code of our project is primarily located in the dashboard and BT Audio TRX folders under the sample directory. You might wonder, What is BT Audio TRX? Actually, our dashboard application is built upon it. BT Audio TRX itself is a versatile Bluetooth solution supporting audio transmission, device control, and more. Full documentation is available on our Real MCU website. Additionally, the flash map configuration files are in the Flash 16M directory. If you use 32 MB or larger flash, simple configuration adjustments will make it compatible. The system architecture is like a three-story building. The foundation is hardware including peripherals, Bluetooth baseband, and RF modules. The middle layer contains FreeRTOS, drivers, algorithms, and Bluetooth protocols, like generic access profile or generic attribute profile. The top layer is the application level, your main area for customization. All information, battery level, Bluetooth status, speed, turn signals, ultimately converges on the GUI. Data comes from diverse sources, motor status detection, Bluetooth commands from phones, and direct user inputs, all flowing through the layers to the display. The RTL8773 EWP chip runs in RTOS with enhanced customization. It natively includes critical tasks like timer task, idle task, flash task, and Bluetooth protocol tasks, controller and host. Our dashboard extends 4 tasks, including app task, GUI task, and communication send and receive task. Communication send and receive tasks manage device phone interactions. The receive task parses incoming data like unboxing packages, while the send task packages and transmits outgoing data. The GUI task handles interface refreshing. GUI updates are typically triggered by specific events, such as keystrokes, timer expirations, or other application behaviors. Before refreshing, we update all control information based on the current system state to ensure accurate on-screen display. The core GUI components are then rendered into the frame buffer according to their types and positions. We provide 2 frame buffer implementations, RAM blocks and PS RAM full frame. When using internal RAM as the frame buffer, we divide it into multiple small blocks to conserve resources. In the current SDK, each block contains 10 pixel rows, totaling 48 blocks. Each block is synchronously sent to the screen via the LCD controller immediately after rendering. For systems with PS RAM, the entire frame buffer can be stored in PS RAM to leverage its larger capacity. All controls are first updated to the full frame in PS RAM, then transmitted to the screen at once through the DPI, display pixel interface. This approach simplifies implementation, delivers higher refresh efficiency, and is our recommended solution. In summary, our solution offers 3 key strengths: flexible feature customization via macros, dual frame buffer strategies for hardware optimization, and end-to-end toolchain support from building to validation. For deeper technical details, please refer to our documentation. That concludes today's presentation. Thank you.